At the afternoon session, we will have a colloquium open for the Institute. I have the pleasure to introduce Igor Shovkovy, who's a participant in our workshop on electromagnetic effects in strongly interacting matter. So he kindly accepted the invitation to give the colloquium, so thank you, Igor. I have here a very brief bio of Igor. He was actually very modest on the bio he sent me, but I will read that. So Igor Shovkovy is a professor in the College of Integrative Sciences and Arts at Arizona State University. He received his doctoral degree in theoretical physics from the Bogolyubov Institute of Theoretical Physics in Kiev, Ukraine, in 1997. He had postdoctoral training at the University of Cincinnati, University of Minnesota, and Johann Wolfgang Goethe University in Frankfurt am Main. Before joining Arizona State University, Dr. Shovkovy held a junior fellow position at the FIAS in Frankfurt and an assistant professor position at Western Illinois University from 2006 to 2008. His expertise includes theoretical nuclear physics, high-energy physics, and condensed matter physics. He's one of the co-authors of the book Electronic Properties of Dirac and Weyl Semimetals, published by World Scientific in 2021. I would add he's author of several reviews and more than 150 papers in the field, and accumulate more than 8,000 citations. So I think for the people from the field, he doesn't need an introduction. So thank you very much, Igor. So,
well, I have to thank you for the invitation. It's my great pleasure to be at this institution. It's the second time, the second issue of this conference, and I'm really very glad to participate and meet everybody in person. So I will be talking about the properties of quark-gluon plasma, and of course we all know and we love it because that's a new state of matter that was discovered primarily in Brookhaven in heavy ion collisions. Of course, quark-gluon plasma, or more exactly quark matter, may exist also in the dense regions of the compact stars. So that's the picture on the right, and this middle panel shows the phase diagram of QCD that we could potentially explore in different applications. And what I'm going to talk about is primarily about that top left part of the phase diagram, which is also relevant for the cosmology, for the early universe, and of course this is the probe of the phase diagram, which is primarily probed in heavy ion collisions. So quark-gluon plasma is a new state of matter. We cannot see it so easily because quarks are confined, and we only see their products in the form of nucleons, protons, neutrons, and of course nuclei that they form, and so on. So of course it's very interesting to find a way of probing that fundamental new state of matter. Heavy ion collisions, they are having very, very simple idea. You have large nuclei collided at very, very high energies. As a result of that, you produce essentially extremely hot, high entropy matter, which presumably quickly equilibrates to form a fireball of quark-gluon plasma that evolves through several different stages. Some people call it little bang, resembling the Big Bang of the cosmology. And of course, we have access to probe and test what is formed through all kinds of particles that are being produced in these heavy ion collisions. One of the things that you will notice that at almost all the stages of this collision, you have a lot of photons produced. Well, basically, it shines. It's very hot matter, and it produces all that light that we will see. And one of the things was originally as a goal in exploring this state of matter is how to probe its temperature, how to probe its properties. Well, when you talk about something as basic as temperature, you could basically do the same you do with a child when you measure temperature without touching the body. You use thermometer and basically point at the forehead and measure the temperature. We basically do exactly the same with the heavy ion collision. Of course, we have to have a slightly better design for that probe. Other than that, the idea is the same. Now, theoretically, as I said, photons are produced in all of those stages of the collision. And of course, you will get a mass of different photons produced in the quark-gluon, before quark-gluon plasma forms, during the formation of the quark-gluon plasma, when the plasma equilibrates, when it cools down, when the hadrons form. All of that is basically shining hot stuff. And we will see photons coming from that. The good thing about the photons is, and that is sort of tacitly known by everybody working in the field, but maybe not everybody from outside of the field, is that actually those photons are relatively weakly interacting with the rest of the matter. And since the density of that matter, even though it's high, because of the size small, those photons essentially escape almost immediately after they form, because the scattering length is larger than the size of the actual fireball. So you have all of those probes coming from different times of the collision. And of course, in the experiment, you don't really know if this photon came from the very early or from the very late of the collision. So the only indirect measurement of that is the range of the energies, or in this case, the so-called transverse momenta of those photons that you measure. And then in different regions, theoretical models predict that different types of the photons are dominating, coming from one or the other source. In particular, I will concentrate on this part of the photons with the energies or transverse momenta less than about 2 GeV, which will correspond to the region where the thermal QGP photons dominate, the so-called direct photons that I will be talking about. A little bit of theory about that, how to calculate the emission rate of the photons from the quark-gluon plasma is a relatively known strategy, and the approach goes back to the 90s. One of my mentors was actually the first author who provided the theoretical description of this. You could write the rate of the photon emission in terms of the imaginary part of the corresponding electromagnetic current correlator, or the so-called polarization tensor. So you could write diagrammatically the calculation that comes from calculating the imaginary part of some diagram like this. This is the simplest one-loop approximation. When you have the photon incoming, then the quark loop, and the photon going. The imaginary part actually can be understood in terms of these diagrams by something called cutting those diagrams. So roughly speaking, if you cut the diagram, you will get the diagram for the processes that come out of that. And in fact, this first diagram gives nothing in the case of calculating this rate, because that imaginary part will be 0 for the reasons I explain later. Essentially, the conservation of the energy and momentum cannot be satisfied. And those diagrams, when you cut, you will see there are 4 lines essentially remaining, this one end line, and at the point of the cut, there are 3 more lines. And they essentially translate into calculating those processes. The processes are very simple. When you have a gluon and the quark coming together, the quark goes through, the photon is replacing the gluon, and that's essentially the dominant process that happens in this calculation. So this is the types of the diagrams that dominate the production of the photons in the quark-gluon plasma, and you could calculate them relatively easily. That's what was done in those papers. So this is even the analytical approximation. The numerical result is slightly different, but essentially that was understood and done a long time ago. That's the message. We know how to calculate that spectrum. If we see something like that in the experiment, we could measure the temperature, because it, of course, changes with the temperature. Now, later it was understood that's not the end of the story. There are complications. There are subleading order diagrams. And when I'm talking about subleading order diagrams, I'm having some specific processes. I don't want to go into details at this point, but it suffices to say that actually those are very large contributions. In fact, in certain regions of the energies, it could be giving the corrections as large as 100% compared to the leading order contributions. So that's the sort of the generic story, but more or less it's under some control. There are a lot of theoretical studies done that can calculate this process as well. Where we have a problem is actually not so much about the rate of those photons, but the distribution in terms of the isotropy. If you look at the production of the photons, you will see that in the reaction planes, in those directions, there are more photons, more energy emitted than in the direction outside of the reaction plane. And that is the so-called large V2 problem. So if you look at the ellipticity, the amount of the energy deposited is not isotropic. That's the bottom line. In fact, the non-isotropy is very large. Naively, originally, people thought if the plasma is evolving like a bubble of sorts, hydrodynamic type of matter, then maybe that non-isotropy of the bubble will create this non-isotropy in the photon emission. There is a problem with that, and the problem with that essentially those photons that are emitted at the very end, where this non-isotropy is well developed, it's too late to actually have sufficient photon production. So in fact, the photons are produced early on, relatively early on, when there is no that ellipticity in the system, and you would expect pretty much isotropic emission. Naively, that's the theory, but that theory is failing badly behind the actual experimental data. The experimental data shows that there is high anisotropy, and there is no good explanation of that. So that's the big problem that was facing, is still facing us. So what's the resolution of that? Well, one of the proposals that exists right now is actually that perhaps it is somehow related to non-isotropy of that plasma that we have. And it's not due to the ellipticity of its expansion, but actually due to the presence of something else, in particular the magnetic field that may exist in that plasma. And of course, the magnetic field will be out of plane. That gives you the anisotropy. Will it give the enough anisotropy to produce this photon emission that is so anisotropic? That's the question. So where do we get the magnetic fields in heavy ion collisions? I believe it's relatively easy to understand for anybody starting from high school physics. If you have two currents passing each other, in between those currents, you will have the magnetic field perpendicular to the plane in which the currents are flowing. So that plane is the reaction plane. This is one current. This is another current. Here you would have the plasma formed and the magnetic field potentially inside of that plasma. By the way, I said potentially because that's another issue that I'm not going to touch very deeply on, because how much of that magnetic field remains in that plasma is a big issue. Anyway, that's the situation we have. You could calculate the electrical and magnetic fields that are created by those currents. Of course, this is not a steady current like you do in, I don't know, first year of undergraduate studies. It's a little more complicated because they are moving fast past each other. There will be time-dependent magnetic and electric fields. So it's a little more complicated. But you could write down the potential that comes out of that, the electrical and magnetic fields, basically immediately, then consider how many protons you have, and basically put everything on a more or less solid footing. So you could calculate that, and people did that. In fact, this problem was revised and re-looked at by many different people, considering all kinds of complications that are possible. There are fluctuations of those charge distributions. There are fluctuations in how we determine the reaction plane versus what we see in the particle detectors and all of that. So you could find the detailed analysis of that, all of that. But all of this falls a little bit short to be confident that we really know magnetic fields. And the reasons, of course, there are many reasons. The reasons are that there are these fluctuations, the fields are inhomogeneous. The fields, if they were in vacuum, they would drop out very quickly after the collision. If it is trapped inside of the plasma and it stays with the plasma, they may live a little longer. But all of those are very big theoretical uncertainties we don't know good answers to. So one of the things that I was thinking about recently, over the last several years, in fact, that perhaps we can probe that. And we can use some magnetometer, if you wish, just the same as we use the thermometer to measure that. Well, this kind of device doesn't work. unfortunately. The magnetic fields are actually existing on very, very short time scales. We cannot really have any permanent magnet placed like that near the collision, so obvious difficulty there. But an interesting thing is that those photons and, in fact, as I will tell you later, dileptons that are closely related to the photon rates, they will be actually carrying information about the magnetic field just the same as they carry the information about the energy. And the information they will be carried on will be two things: modified rates and the ellipticity of those emissions. And that's exactly what I'm going to tell you about, and that's the story, the rest of the story here. So theoretically, calculation of the photon rate goes back to essentially the same leading order calculation that was presented in those early papers starting from 91 by Kapusta and others. So you still need to calculate the same thing. The complication comes in the form of the modified polarization effects in the presence of a strong magnetic field. It's not the same as without the magnetic field. And in fact, there is a surprise. The surprise is that, in fact, that leading order diagram, the simplest possible diagram that you could write for the polarization tensor, in fact, gives a non-zero contribution already in the presence of a magnetic field. The reason is that when you cut this diagram, then you will see that it really reduces down to these three diagrams. It's essentially quark splitting off a photon and continuing like a quark, anti-quark doing the same thing, or annihilation quark and anti-quarks into a photon. You might say, why didn't I consider this at zero magnetic field? Well, at zero magnetic field, all three processes are forbidden by the energy momentum conservation. It's not possible at all. In the presence of a strong magnetic field, in fact, these rates are large. And provided the magnetic field is sufficiently strong, these are leading order diagrams that will dominate the emission. So you could make the interpretation of what exactly is happening, how you calculate those diagrams. If you are a little more interested in condensed matter physics, you could rewrite all of that information in terms of transition between the lines like you usually do in condensed matter physics. Since I was working both sides, to left side of my brain, probably those diagrams talk better. To the right side of the brain, those pictures look better. So whichever taste you have, basically that's the diagrams and interpretation of what is happening. Now, the energy momentum conservation in the presence of the magnetic field is different than without the magnetic field. And the reason is that we do not have any momenta well defined in the plane perpendicularly to the magnetic field, which is obvious because if the particle tries to move perpendicularly to the magnetic field, it will start going in circles. And of course, that means that the momentum, if it was px, will not be any more conserved. It will become py, then negative px, then negative py, and it changes all the time. In fact, that is not a good conserved number. Instead, you have the so-called Landau levels, and that index is basically levels 0, 1, 2, 3, and so on. And the conservation law looks like follows. Not only it's relatively simply looking equation, you could actually solve it analytically and calculate everything you want. And this is the result that I'm going to present to you. So what is shown here, I calculated the differential rate for the photon emission as a function of the angle phi, which is measured, in this case, from the reaction plane, which is this double yellow line. So this is the reaction plane. And remember what I told you in the experiment. You see that there are more photons emitted in that direction of the plane and a little bit less outward in the direction perpendicular. Now, if you look at this rate, that's basically the rates, and this is a slightly different representation that gives a better impression of the geometry of the emission. And if you look at that, you immediately appreciate that's totally wrong, because there is obviously more emission in the direction perpendicularly to the plane rather than in the plane. There is one subtlety here, however. The reason it's like that, as I will explain later, that here I'm considering relatively small transverse momenta of the photons. And in fact, there is a very, very good explanation why that is happening. So basically, I have much more radiation in the direction 90 degrees perpendicularly to the plane. If I consider the rate at larger, and notice it's still well below those 2 GeV I told you about, you will see that for those larger values of transverse momenta, the picture completely transforms. In fact, you do see the emission going primarily in the direction of the reaction plane. And that is nothing else but the sign of the positive V2, or ellipticity, that is in agreement with the experiment. So what is happening here is the following. If you look at the ellipticity, so the characteristics for the ellipticity is the coefficient in front of the cosine. If you write that emission energy as a function of the angular coordinate, there will be a certain cosine, 2 phi or something like that, and there will be a coefficient measuring the degree of the ellipticity. So that is the so-called V2 coefficient. So if you look at the dependence of that coefficient on the transverse momentum here, you will see that something is happening somewhere in the middle. It starts with a very large negative V2 at small kt, then passes through 0, and then becomes positive, and in fact substantial, 20%. That's a very, very large ellipticity. So what is happening here is the following. This is the scale determined roughly by the value of the magnetic field. If the magnetic field is fixed, then this kt point where the crossing happens is roughly determined by that value of the magnetic field. The stronger is the field, so this is the stronger field, 2 bottom panels, the further to the right that crossing happens. The smaller is the field, the further to the left that crossing happens. So if we were living in an ideal world and we measured the ellipticity all the way to the small transverse momenta, in fact, finding the crossing would tell us immediately about the field. Of course, it's not that easy in real life, but just as a matter of principle. Now, what is happening is there is actually a very simple explanation why all of this is happening. I'm not sure that in the colloquium I will have the time to perfectly explain it. But in 2 words, the explanation is simple. For small energies of the photons, small compared to the distance between the Landau levels, those transitions are not very easy to arrange. Large gap, small energy. Incompatible. To make it compatible, you have to go to the high momenta to make it happen. And to go to high momenta means that you will actually suppress certain directions. And what happens is precisely, you could explain very carefully how that suppression happens, that it leads to the negative V2 at small energies. Then when you go to larger and larger energies, you start to have more or less normal transitions. What you would have is something analogous to the synchrotron radiation, and basically it will give this V2 analogous to synchrotron radiation, but now in the quantum regime in application to heavy ion collisions. And that's your positive V2 that you potentially see in the experiment. Now, there is additional story that goes the same way for the dileptons. Now, dileptons is a slightly different story. What it is essentially the process of this type. So we kind of have similar input. We have quark and anti-quark coming together, forming a virtual photon. That's very important. That diagram is essentially showing you Feynman diagram, but that photon in the middle, it's not a real photon. It actually has the flow momentum such that it produces a pair of leptons, lepton, anti-lepton, like E plus, E minus, and those would be real particles seen in the experiment. So the diagram is slightly more complicated because you have those 2 leptons. It's also slightly more complicated because there are 2 things now, not only the value of transverse momentum where it goes, but also the energy of those leptons together, the so-called invariant mass of those leptons. So we have these 2 complications that come with that. And of course, we could write down again the analytical expression, how to write that dilepton production rate. You could see that there are several parts here. One of these parts, and this is a little interesting to discuss here because it's actually somewhat technical, but has a very simple physics explanation. There is the so-called lepton tensor, which kind of tells you in what kind of states you produce those leptons at the end of the game. The thing is, there are two lines of thought here. One line of thought says, well, you are producing those leptons inside of the magnetic field. So they should be produced just like the quarks in the magnetic field, not like freely propagating particles in space, by like circulating particles in a magnetic field in the Landau levels. This formula assumes tacitly, and that's something that only experts can tell, tacitly that I'm looking at the leptons being produced as plane waves. That says I'm doing something wrong. Well, in fact, it's not. And the reason it's not is there are two reasons for that, actually. One reason is those leptons, they have very, very long mean free path in a plasma at this temperature. Again, just like the photons, they will have the mean free path much larger than the size of the plasma. In other words, they don't have a chance to rescatter. So even if they are produced as particles in the Landau levels, circulating particles, sort of, if you wish, in this yellow region, they have to be projected onto the plane waves as soon as they leave the plasma. Now, in which state they are produced, in first level, second level, 10th level, you cannot tell. In fact, they are produced in any of those possible states. But the thing is, you have to sum up over all of them and then project each and every one of them on the plane wave. But in fact, that is totally equivalent. Because if I take the full set of my in-magnetic field states, they will sum up and give you exactly plane wave states as soon as you get outside of the plasma. And since we are measuring the leptons in the detector as plane waves, as particles with given momenta, in fact, it is only this state that matters. All of those intermediate things, they are basically irrelevant. So when I'm writing this amplitude, I'm essentially tacitly assuming that I performed that sum over all possible products inside the magnetized medium and then immediately projected them out simply because they didn't have any time to rescatter. And that's, I believe, the only correct way of addressing the problem. So basically, resolving that issue was one of the main obstacles in this calculation. The other one is writing down the so-called electromagnetic spectral function that, not much of a surprise, is given in terms of the same imaginary part of the polarization tensor, although the energy and momentum inside of this tensor are not related to each other, just like in the case of the photon emission. For the photon emission, this omega squared was equal c squared k squared. For the dilepton production, it has to be giving you the so-called invariant mass, because the particles from the kinematics, they have non-zero masses, and essentially you have to consider what happens in terms of the dileptons, and that basically changes this a little bit. But other than that, it's the same formal calculation. So you could write down the expression for that rate in terms of this polarization function. You could calculate the polarization function. The calculation is a little more complicated, but still doable. And essentially, you reduce down to the same processes. But the only difference is this, you see gamma star basically means it's not on mass shell photon, or basically not a real photon, but a virtual one that turns into leptons. So I will not bore you too much with the calculation, except that saying that there is that calculation done. And I should have erased this slide, but apparently I forgot. So anyway, the important part about that is the following. If I had to summarize all of that mass on the slide in terms of words, if we know the distribution of the quarks in the plasma, so basically if we know that function, which is actually nothing else but Fermi-Dirac distribution function, then basically we know how to calculate those rates. So in principle, what I'm showing next implies that I'm considering the plasma in quasi-equilibrium when the distribution of the quarks in energies is essentially the same as in equilibrium with a given temperature that is characterizing that plasma. With that said, this calculation easily modifiable to the so-called pre-equilibrium conditions where you have some distribution of the quarks in the states, but it's not necessarily Fermi-Dirac. So that can be also modified, and of course this distribution function has to be changed to something else. Other than that, of course, you could do the same calculation. And of course, there are a little more complications here coming from the fact that we have some, if you wish, form factors that depend on all of those momenta. So that's not an important part that I want to emphasize. But what I do want to emphasize that if you write something as complicated as that, and you're trying to convince anybody that it's trustable, one of the things that you should do is to make sure that it makes sense. And one of the ways to make sure it makes sense is actually to consider that result to something that everybody knows. And something that everybody knows is that in the limit of 0 transverse momentum, I could write down all of that mass, all of that complicated result in terms of just two simple quantities, the so-called magneto-optical conductivities along the direction of the magnetic field and perpendicular to the direction of magnetic field. And in fact, even if I didn't have to do it in high-energy physics, I could have quoted these results from condensed matter physics with some minor modifications. So in fact, that is well-known result, and I could find them. In fact, I could calculate it from our calculation of the polarization tensor in that case. Oops, wrong button. And you will find that those conductivities take very, very simple form, something as simple as that. You could take, that's in the limit of the 0 magnetic field. So if you compare this with the well-known result of the 0 magnetic field calculation for the same rate that is also known, and if you compare the two, this result here and this result there, you will find that it's exactly the same result. And it's the 0 magnetic field case written here. And if you find this rate and this in the limit of k goes to 0, that are coming from drastically different calculations, from drastically different things. So this is from non-zero magnetic field limit and using all of those intermediate formulas. And this is original old result that goes back to late 80s. They perfectly agree. So that's a good cross-check to have in mind. And basically, then we can continue and see what this result tells us. So if you look at the dilepton rates, as I said, there are some minor technical complications. You have a little more freedom. You have the momentum, transverse momentum of this lepton pair, and you have the invariant mass. And of course, those are basically like two independent parameters, so you have to be careful analyzing it. And of course, you have to translate all of that in terms of some quantities that are a little more reasonable for heavy ion collisions. So that's basically what I did, calculated those rates as a function, in this case, of the invariant mass for several fixed values of transverse momenta. So there is a lot of information there, but basically what you want to see is just a few small things. One of the things that you would want to immediately pay attention to is this side. Why? Because here I'm comparing the results at 0 magnetic field, that dashed line, like this red dashed line, green dashed line, and so on. So that's essentially the old result from late 80s. And the result in the presence of the magnetic field. Immediate thing that you see that the magnetic field gives huge enhancement of the rate at small invariant masses. In fact, what means small? Actually, same thing. Scale determined by the value of the magnetic field. For those invariant masses smaller than, roughly speaking, the scale given by the magnetic field, you have an enhancement orders of magnitude. So in this case, 2 orders of magnitude. For the black line, I believe it's like 4 orders of magnitude. And of course, that enhancement actually kind of interesting. It goes up and then it goes down. The peak actually I could determine also, estimate its value. It's also determined by the ratio of the magnetic field and the temperature. But the most important feature, it's actually having huge, huge enhancement in this region. So this is one of the things that if you measure, you will be able to tell the value of the magnetic field. Of course, that enhancement changes with the temperature. It's actually changing with the magnetic field. But I guess I won't show that result for the magnetic field. Also, you could even calculate very easily analytically this enhancement. This is the actual simple, very simple analytical formula that is describing that nearly perfectly. The dashed line is this formula. And the black solid line is the actual numerical calculation done carefully. So what you learn from here is, first of all, that we have some theoretical control of these calculations. Secondly, in the absence of the magnetic field, we do approach the zero magnetic field result. By the way, for the large values of the invariant mass, we do reproduce essentially the rates that are supposed to be in the zero magnetic field. And the reason is that when the invariant mass is so large, the fact that there is a small magnetic field basically irrelevant. It really becomes relevant only for the small invariant masses. So you could calculate also that was the total integrated rate. So the total amount, how much you produce. You could also, of course, calculate the differential rates. So as a function of the angular coordinates, same definition of the angular coordinate, how the rate change for different values of kT again, and fixed value of the invariant mass. Notice that I took a relatively small value of the invariant mass precisely because that's the region where the effect of the magnetic field is the strongest. So that's where I'm expecting to see something interesting. And maybe you cannot see immediately, but actually you should if you pay attention, because this is logarithmic scale. The emission here in the zero direction angle is considerably larger than in the direction at 90 degrees. 0 is in plane. 90 degrees is out of plane. So actually, you tend to produce those dileptons in those directions in the plane much more than in direction out of the plane. And this is actually looking a little bit messy, but it carries that information that I just said. This is the ellipticity of dileptons as a function of the invariant mass, and this is where everything interesting happening. That's where you have relatively large, by the way, also comparable to the photon ellipticities on the order of 20%. It's huge. And in that sense, it's a very distinctive feature due to the magnetic field. So the ellipticity is large in that region, but of course, with additional constraint that this is really only working for relatively large transverse momenta. And that is perhaps not as obvious from the picture, because I already took here the values of substantial values of kT. For the blue line, which is the smallest, you start to see that it might be failing a little bit. And in fact, it's sort of could be interpreted as a virtual synchrotron radiation in some sense. So it's not the same, of course, because it's quantum calculation, not as typical synchrotron radiation done in a classical approximation, but it's sort of related to that. And of course, we see that that happens across different temperatures, also across different values of the magnetic field. And this is how it looks like if you plot it in a polar coordinate so that you could see visually that that emission is pretty elliptic, with the positive ellipticity, meaning the emission is going primarily in the reaction plane. So that's one of the distinctive features that I wanted to emphasize. And of course, it's working pretty well for different values of the magnetic field. So that was, if I go back, for a smaller magnetic field, for larger magnetic field. In fact, you could go even to smaller magnetic field, and you still see that. The only problem will be that you would have to go even to smaller values of the invariant mass. There is also a lot of details. I'm not sure I want to talk about that, but if anybody's interested, there are zillions of those little spikes. and that is the so-called threshold effects. And basically, they will be all smoothed out when you actually put it in realistic calculation of heavy ion plasma. And I will not go into details about the reasons for that, but essentially, whenever you see any of those spikes, think of smoothing them out and making them less pronounced. So that works for small invariant masses, but not so much for large invariant masses. So if you consider the same rates for a bunch of different values of larger values of the invariant mass, you will see that the emission is pretty much flat. There are still a lot of those spikes. They will smooth out, as I said, so don't pay too much attention to them. But if you look at the general profile after averaging, you will see that it's pretty much nearly isotropic. And that's precisely the limit where there is still relatively large effect of the magnetic fields in those spikes, but not so much in the anisotropy of the emission. So that emission becomes pretty much isotropic. And overall rate, I should remind, also approaches the zero magnetic field limit. So that's true for different values of magnetic fields, and basically it works in all the cases. Now, to summarize all of this, I basically have a very simple message here, basically telling you that we could potentially use electromagnetic probes as a magnetometer for measuring the values of the magnetic field in the quark-gluon plasma, when the thermal emission of the plasma is replaced by the thermal emission of that same plasma with the strong magnetic field present in the system. And the feature that we want to see is essentially this unusual characteristics of the emission that I just presented. One of them is the dependence of the ellipticity of the photon emission. In the case of very small transverse momenta, which, by the way, experimentally is probably completely unrealistic to detect because you would have to go to very, very small momenta. But in the relevant region up to 2 GeV, and I'm pretty sure that we cannot generate magnetic fields as strong as that. So basically, we will be safely in this regime, and we will have relatively large anisotropy with large effective ellipticity of the photon emission. And I should emphasize, and this is probably the most important message, that this is coming from isotropic fireball of the plasma. The only anisotropy is set by the magnetic field in that system. And that's the result of that anisotropy. And you don't really have to rely on the hydrodynamic evolution of the plasma to develop large V2 and produce such emission. So this non-zero emission, and ellipticity is going to be one of the potential signals for the magnetic field. And in fact, the measured value, large V2, which is the so-called photon puzzle, is potentially related precisely to this. And for that matter, I should probably emphasize, it's hard to estimate from that V2 the actual value of the magnetic field, but it's probably relatively safe to say that even relatively small magnetic fields will give you this synchrotron radiation that is essentially going to give this large V2. And perhaps even cleaner signal is coming from the dilepton emission, because in this case, not only we have a clear excess of that emission relative to the zero magnetic field case at small invariant masses, but also a relatively large V2 that will be produced just in the same way as for the photons. And in fact, as far as I know, there are experimental attempts to actually tackle this problem and measure the V2 reliably enough, and potentially that will also show that the ellipticity of the dilepton emission is large. It cannot be due to hydrodynamics, but it can be due to the presence of the magnetic field. So that's essentially all of that that I had. In the case of the V2 at large invariant masses, unfortunately, it's relatively small. So we cannot go for those large invariant masses to see something really interesting. But this would be a smoking gun that there is a strong magnetic field. So, and with that, I basically want to finish saying that the electromagnetic probes, such as the photon emission and the dilepton emission, are potentially the magnetometer of quark-gluon plasma. And if measured carefully enough, we will have the information about the magnetic field in the quark-gluon plasma. And with that, I'll stop. Thank you.
Thank you, Igor. Very nice and entertaining talk. I have many questions regarding some of the assumptions that you made and your results. Some of them you already answered in the summary, but I had a couple of other which you may have some insight. I do agree that if you sum over all of the Landau levels, as you said in one of your transparencies, the final state of the dileptons is a plane wave, right? One of each one of them. However, I'm concerned that if you're considering the effect of magnetic field, and as far as I understand, it's not that small, it's on the order of the pion mass squared, if I am reading correctly your numbers, which is another issue for the time when there is already a thermal state, but in any case, it's strong enough to bend, thank you, it's strong enough to bend the trajectories of the dileptons in such a way that perhaps what you're measuring, particularly for small PT or invariant masses as well, you can do cuts in PTs for the dileptons, then you will see some other kind of broadening kind of structure of your dilepton spectrum. So can you comment on how you can estimate this extra KT kick?
Right.
And the second is, and I'm surprised that your V2 for dileptons has the opposite behavior as your V2 for photons, whereas in my mind, I may be very, very naive, in my mind, one is a real photon and the other one is a virtual photon, so the characteristics should sort of inherit to the dilepton spectrum. So 2 questions in a shot, sorry. Yeah. Thank you.
Well, it's actually good questions. We thought of them, and I have clear answer to both. The first question about the substantial part of the dileptons inside of the plasma. The good thing about that is that this dilepton pair is a neutral state as a whole, and that means immediately that if there are no rescatterings, that momentum, virtual momentum carried by the photon, is exactly the virtual momentum of the dilepton pair because it's a neutral state. So they diverge kind of like this, but essentially the momentum remains exactly the same. And that means that there is absolutely no broadening at this level, but you have to consider maybe higher order corrections. So that is the first question. The second question was about
why the dilepton V2 shows characteristics?
Right. Actually, there is no also big difference because actually both of them are large positive V2s in the relevant kinematic region. In fact, in the case of the dilepton, there potentially is a possibility that an extremely small KTs, it may change the sign also to become negative, but that's extremely low values, and in fact, in some cases, we simply didn't have enough precision to reach this region for all the cases. But this blue line is kind of indicating that at extremely small KT, you may have this rate happening as well. But the thing is, it's irrelevant for the experimental data because we are going to be sitting somewhere here. And the other thing is, when the magnetic field is even smaller, this still remains. This still remains, and it's essentially not so critical if you have super strong magnetic field or not, because that contribution is coming not from one level or two, it's coming from essentially very, very many levels at the same time. So in relative terms, in fact, these are small magnetic fields, because if you consider the corresponding temperature and magnetic field, so like T squared and EB, they will happen to be something like 6 to 10 times different, especially for some cases. So it's almost like weak magnetic field. So, and we can push to even smaller fields, and basically it seems like it will stay the same, but numerically it's expensive to do.
So let me take the opportunity. So this kind of negative peak that is persistent, this is not physical. So this is just
here?
Yes.
No, this is basically fluctuating, and it will all smooth out nearly to zero.
It's in the same place for
No, it's the thing is, because of those spikes, we have essentially the Landau levels which are of zero width. And because of that, you have the so-called threshold effects. And sometimes they spike one way, sometimes the other. And basically, that is all going to be smoothed out as soon as you introduce any interaction effects in the plasma. So that is basically implying that all the large spikes, they will smooth out to a smooth curve. Here, that smooth curve will remain above zero. Here, it will go to zero.
So you're doing that, or you?
Not really. But I know how to do each and every one of them, yes.
When you have a student.
Yeah.
Thank you, Igor, for the captivating talk. Now I really feel like I would like to sit down myself and calculate that polarization tensor. So did you consider not just the effect of magnetic field, but electric fields for this calculation? And how do you know it has to be the magnetic field which is the relevant one? We learned in this workshop that electric fields are also there in the early stages.
Right. There are certain ideas how the electric fields are potentially going to modify this. And generically, if you have large scale on the scale of this plasma electric fields, typically what they do, they shift the distribution functions. So they do not create any increased density of states like the magnetic field is doing at small energies. So the kinematic, presumably, and I didn't do the calculation, but the thought idea was that presumably the only thing that it does, it actually only changes the distribution of the quarks in terms of boosting the distribution functions to other values of the momenta. And that doesn't seem to offer any interesting features. The magnetic field is doing something very interesting because of two things. It opens the phase space, and it increases the density of states at low energies. And those two things together, they actually play a huge role here.
Thank you for your talk. It was very interesting, and I have two small questions. The first one is, can you speculate what the time dependence of the magnetic field would mean for your results? Since in the beginning you said it's short-lived, and very smoothly it became constant, I guess.
Here's question. Yes, it's the biggest problem. In fact, the thing is this. The magnetic field could be as large as of order m pi squared, as I was using calculations, or it could be maybe 1,000 times smaller, and we don't know that. So the idea is that if this magnetic field was trapped in the plasma, as usually in a conducting plasma you would have the magnetic flux preserved, then this would be the effect that we would expect. If we don't see any of this, then basically the fact that it was a short magnetic field in the early stages wouldn't matter at all, and we would have the rate that is essentially the same as without magnetic field. So here I'm not really offering the proposal that there is a magnetic field. I'm saying if it were, what it would tell us.
Maybe related to that, I guess not in this room, but in the community, people are doubting there's a magnetic field. Could you speculate what else could explain the anisotropy in the experiments?
Well, I don't know. Well, first of all, there could be pre-equilibrium processes that we don't fully understand, because this Glasma ideas and all of that, they are not exactly isotropic in some sense. There are also some potential E.B fields present there, color fields, but nevertheless they could have predominant geometry, and all kinds of things could happen. So I don't really know. I could potentially speculate, but frankly, all of that will be a stretch.
Okay. Thank you.
Hi, Igor.
Where's the
Here,
chairwoman?
on the side.
Oh.
So thanks a lot for the very nice talk. You kept me awake after lunch and having woke up early for my flight. So thanks a lot for that. And I didn't know these results. I'm very impressed. I have a very naive question. I mean, naively, I would expect that one would need a full magnetohydrodynamic calculation in order to compare this production to, real data. From what you said, I would guess it's not really necessary. Do you have a simple physical explanation for this?
Well, the simple physical explanation is this. There is V2 puzzle. That V2 puzzle means that essentially people did try what you said, essentially hydrodynamics, without the magnetic field, so it's not magnetohydrodynamics, but hydrodynamics, and it fails for a simple reason. You develop V2 in the hydro at the late stages of the collision, and the direct photons are coming primarily from the early stages. Mm-hmm. So where it comes, nobody knows. So that was the motivation, if you wish, to check what magnetic field can do. And in terms of magnetohydrodynamics, essentially this is magnetohydrodynamics. And the reason for that, me saying that is that the magnetic field.
But then you would have to have dynamics in the field too, right?
Sorry?
You'd have to have back reaction and dynamics of the field too, I guess. Right?
Yes, it's true. But the thing is, it is the local distribution of the quarks at the moment of the emission that only matters here. So how it evolves, of course, that needs additional simulation. So I would have to implement this, put this at different stages of the collision, take some kind of expansion model, consider how my magnetic field drops with the time, and kind of everything simulate more carefully. So we didn't come to doing that yet. Of course, that's a natural next step. But right now, it was basically the hope to see if there is even a chance.
No, sure.
And
I mean,
that was the answer,
the
yes.
fact that you have a constant field is not so weird, I think, because you're thinking about the preliminary stages where it's kind of flat, right? So
right.
I'm kind of convinced it is.
And as I said, you don't really have to take that this is truly equilibrium. The thing is, if you have a sufficiently strong magnetic field and some distribution of quarks, so I am assuming that the quarks do play an important role because they are basically contributing at leading order in the coupling, then this will all play out. As if, for example, as Alejandro was presenting, if there are essentially almost no quarks in the very early stages, you have only the gluons, all of this will not work. So I need quarks to be present there. The actual distribution doesn't matter so much.
But any distribution, right? It doesn't have to be equilibrium.
Yeah, exactly.
Right? Okay. Thank you.
Thank you, Igor. A very short comment. In all this calculation, the magnetic field is taken as a constant field, especially in spatial. I mean, of course, it decreases in time very rapidly. But we have starting since a couple of months to look at the possibility of having the background constant field plus fluctuation, spatial fluctuations. And perhaps this could also have an effect on the anisotropy that you make.
I imagine yes. I imagine yes, but you have to be a little bit maybe more precise about what fluctuations you allow. Because if the fluctuations are isotropic, then it's not so obvious that something will change. But if the fluctuations themselves are in non-isotropic because of the background magnetic field, then it also changes the results. So there are a lot of complications. Unfortunately, I'm not able to answer
No, of
this
course.
point.
It was just a comment about something possible. Thank you.
Okay.
Yeah, one thing I really didn't understand very well is that in this condition where you have really large ellipticity, you have a strong magnetic field comparing to the best. So you should really have maybe only 1 or 2 Landau levels occupied because you have a strong magnetic field. So you have really strong quantization. So how you say that after this is not important and you can really see that all the states, Landau states are occupied.
Very good point.
So that was something, because I think that this is exactly the quantization that is producing this effect.
Right.
So
no, it's not only quantization.
Okay, so explain me that.
I'll give you a very simple explanation.
Okay, thank you.
Well, first, one of the results. One of the results is the results at very small energies, very small invariant mass here. This dashed line, given by this expression, there are no Landau levels here you could find. In fact, here it's nearly infinitely many Landau levels that contribute at very strong magnetic fields compared to the energies of the emitted dileptons. So you might say, why? Why? Because at small energies, where the transitions between the Landau levels require very large energy of dileptons, nothing happens between lowest Landau levels at all. It all happens in the part of the Landau levels which is at very large momenta and very large n values. Because only there the separation between the Landau levels is close enough to allow these processes. So it's a very strongly suppressed process, especially at very small energies. It goes to 0. But there is an optimization issue here, and the maximum happens like there somewhere. And in fact, you could estimate how many Landau levels you have to calculate for a given virtual energy or the real energy of the photon. So for the large energies, for large energies, you have to sum the number of Landau levels that basically open enough phase space, so you would go to very large N, because you need to reach sufficient energy for this transition to happen. For very small energy, you also have to go to very large N's, because it's only there that the discretization between the energies is small enough to allow that process. So it's all about the phase space where it happens. You cannot just take strong magnetic field, lowest Landau level, and be happy. And that's why it complicates this calculation so much, because we have actually the limit for a given very large number of Landau levels. We take like 1,000 or something. We find what is the range of the photon energies that we can calculate reliably without running into issues on both ends.
Okay, I see. Thank you, thank you.
So can you, thank you for the talk. Can you go back to slide 12, I guess?
12, you said?
Yeah, I think so. 12 or 11. No, 11 maybe. No. Yeah, so that one. So would this technique allow you, for example, to reconstruct the spatial distribution of both electric and magnetic field? So in the same way, in this paper that you show, they have a plot with the distributions, and I was wondering if you could do the same thing for both, because they also detect like a very strong electric field in a transverse direction to the magnetic field. So I was curious about it.
So I need a student. The thing is this. I do have a relative program how this could be done. So one has to take maybe an input from hydrodynamic model, another model, maybe Parton model, where you have more or less good understanding how the distribution of the particles happen at different regions in the plasma at different times in the plasma. So consider the whole evolution, and then basically split that into regions with more or less the same value of a given momentum of the overall momentum, so where the center mass of that region is. So boost the calculation into that frame, calculate the rates, boost back into lab frame, see what is the result, and then superimpose the rates from all of this. So it's essentially something that needs to be done. That is not done yet. That's only with the magnetic field alone. With the electric field, strictly speaking, I do not have a good understanding how to approach the problem yet, because in my understanding what it does, it changes the distribution function in certain ways. But I'm not sure if there are some additional effects, for example, analogous to opening the energy momentum conservation constraints and giving some additional rates. So I don't understand that yet fully, to be honest, but if there is an effect like that, one has to explore it separately.
So it's not so straightforward to go from the dilepton photon distributions that you had in the end to the spatial distribution of the
No,
field,
it's not straightforward, at least at this stage at all.
And in this paper, I think they also have an estimation for the scale that magnetic field has to change, and I think it's 1 Fermi over C or so. So
right,
if it was possible, we could compare to that.
Right. Well, there are a lot of issues. The thing is that, of course, this will not be the fields in the plasma when it equilibrates. I assume it might be weaker than this, considerably maybe weaker. So the only good thing is that the calculation that I show, they in fact kind of not very sensitive to the fact that the field should be very strong. And the reason is that this is kind of approaching almost classical synchrotron radiation, which is also highly non-isotropic. And in that sense, the magnetic field could be really weak to still allow this. So that is not critical to have weak magnetic field. What is perhaps more critical than that in weak magnetic field, unfortunately, these diagrams will not be dominant. You will have to go back to the next order in coupling constant and consider the diagrams that Kapusta and others did without the magnetic field. That's the complication.
Thank you.
Hi, Igor. I have a question. So thank you very much for illuminating talk. That is very interesting. And I know that this kind of computation is solid and very established, but the application to heavy ion collision is a bit dirty business, right? And so my question is the possibility about applying your result to the different branch of physics, that is neutron star physics. So have you ever considered some application, possible application of your this imaginary particle production computation to, for example, the gamma ray burst associated with the supernova explosion, or some kilonova electromagnetic, the counterpart of the neutron star merger that is called a kilonova, that is electromagnetic, completely the photon process.
Yeah.
So you have any comment?
I do. In fact, some people from Japan, some of them, Hattori and others, they actually did the vacuum analog of this, and it is applicable precisely for those applications in cosmology. So something like the photons coming from quasars far away, they actually go through the voids with even relatively weak magnetic fields. Same processes can happen, and they do happen, and basically we cannot see the photons with the highest energies, so there is a certain cutoff, and that tells us about the value of the magnetic field that is present in those voids. So it's an analogous thing, but usually what they do this at 0 temperature, and the complication here was to consider something like quark-gluon plasma. And it also would probably have some applications in the context of magnetized neutron stars. Some of that I may briefly touch on tomorrow in a different talk, but you're absolutely right. It's relevant, but some of the things in vacuum have been known for a while.
So just one thing I want to make sure. So your calculation is at 0 density, right? And the finite density extension, is it already done? Or?
Yes, we did. I gave the quote, but I didn't have... well, somewhere I probably gave a quote where we have this at non-zero density.
Okay, okay.
I probably quoted somewhere.
Okay, yeah, really.
But yes, we have the generalization, and in fact, we can separate all kinds of processes in that case.
Last question.
So, thanks, Professor. Do you think the quark anomalous magnetic moment can affect V2 in some way, some constraint?
Perhaps a little bit. I don't think there are large effects that I'm truly aware of where they might be very big effects. So for example, in the context of what I was saying, I really doubt strongly that it will affect the overall rate a lot, or the V2 will be changed a lot. In fact, coming to the previous thing, the effect of relatively large chemical potential, even that didn't affect many of these results, even though the chemical potentials were substantial. And that is sort of similar in some sense because you separate quarks from anti-quarks drastically when you introduce chemical potential. Of course, it's not the same as anomalous magnetic moment for different spins. One thing that it will make, of course, it will split the Landau levels. And those will be, if they are very small, they will be within this so-called smoothing procedure that I sort of mentioned, that all of those spikes will get smoothed out. Of course, if you have some splitting between the levels and it's smoothed out on top of that, it will be a small effect.
Thanks.
At least that's my intuition. I'm not sure. I haven't done the calculation.
Sorry, just a short question. If you consider vorticity in this context, do you expect significant changes? It would enhance, for example, the synchrotron radiation?
Yeah, we have to consider that problem together.
Okay.
I don't know.
Okay.
Let's thank Igor again.
Thank you.